An equation written in the form m of x comma y dx plus n of x comma y dy equals 0 is called a first-order differential equation. It is exact if there exists a single-valued function psi of x comma y. Think of a height surface on a landscape, such that its total differential matches the left-hand side. d psi equals psi sub x dx plus psi sub y dy equals m dx plus n dy. In other words, m equals psi sub x and n equals psi sub y. By the equality of mixed partial derivatives, Clairaut's theorem, we must have partial m over partial y equals psi sub x sub y equals psi sub y sub x equals partial n over partial x. If this condition holds everywhere in the domain, the equation is exact. The analogy is a river flowing over a hill. The water flow vector field open parenthesis m comma n close parenthesis comes from a single potential surface psi. The condition guarantees that the flow has no circulation like a whirlpool and can be described by a height map. If the condition fails, the equation is not exact, but we may still make it exact by multiplying with a suitable integrating factor mu of x comma y. Explanation: to solve an exact equation, we need to reconstruct the potential function psi of xy. The steps are: integrate m with respect to x while treating y as a constant. Psi of xy equals integral of m of xy with respect to x plus h of y, where h of y is an unknown function that may appear because the integration constant can depend on y. Differentiate this expression with respect to y and set it equal to n. Since psi sub y equals n partial derivative with respect to y of the integral of m dx plus h prime of y equals n of xy. Solve for h prime of y, which usually becomes a simple function of y. Integrate h prime of y to obtain h of y. Write psi of xy equals c, where c is an arbitrary constant. This implicit relation is the solution of the original differential equation. The whole process mirrors finding the height map of a terrain when you know the slope in the east-west direction m and north-south direction n. Once both slope components agree, exactness, you can piece together the terrain. Example, for m equals 2xy and n equals x squared, integrate m with respect to x gives psi equals x squared y plus h of y. Differentiate with respect to y gives psi sub y equals x squared plus h prime of y equals n equals x squared, which implies h prime of y equals 0. So h of y equals c sub 1. Hence psi equals x squared y equals c, the implicit solution. Explanation: sometimes the given m and n do not satisfy partial m by y equals partial n by x, but a factor mu that depends only on x can balance the equation. Assume mu equals mu of x. Mu m dx plus mu n dy equals 0. For the new equation to be exact, we need partial of mu m with respect to y equals partial of mu n with respect to x. Because mu depends only on x, we can pull it out of the y derivative. Mu times partial m by y equals mu prime n plus mu times partial n by x. Rearranging and dividing by mu n, provided n not equal to 0, yields partial m by y minus partial n by x equals mu prime over mu times n, which implies mu prime over mu equals partial m by y minus partial n by x, divided by n equals f of x. If the right-hand side simplifies to a function only of x, then we can integrate ln mu equals integral of f of x dx, which implies mu of x equals exponential of the integral of f of x dx. Thus the recipe: compute partial m by y minus partial n by x divided by n, check whether the result depends solely on x. If it does, its integral exponentiated gives the integrating factor mu of x. In physical terms, imagine adjusting the density of a fluid mu that varies only along the x direction to make the flow field become a gradient of a potential. Example, m equals y times e to the xy, n equals x times e to the xy. Compute partial m by y equals e to the xy plus xy e to the xy. Partial n by x equals e to the xy plus xy e to the xy. Difference equals 0, so the original equation is already exact. If we had n equals x times e to the xy plus 1, the difference would be negative 1, and partial m by y minus partial n by x divided by n equals negative 1 over x e to the xy plus 1, which is not a pure x function, so a mu of x does not exist. Explanation: Now look for an integrating factor that depends only on y, mu equals mu of y. The derivation is symmetric to the x case. Mu m dx plus mu n dy equals 0. And demanding exactness gives mu prime m plus mu partial m over y equals mu partial n over x. Dividing by mu m, m not equals 0, we obtain mu prime over mu equals partial n over x minus partial m over y divided by m equals g of y. If this ratio simplifies to a function of only y, then mu of y equals e to the integral of g of y dy. The interpretation is similar. We are thickening or thinning the fluid only along the y direction to turn the flow into a conservative field. Example, m equals 2xy plus y cubed, n equals x squared plus 3xy squared. Compute partial m over y equals 2x plus 3y squared. Partial n over x equals 2x plus 3y squared exact. If we change n to x squared plus 3xy squared plus 1, then partial n over x minus partial m over y equals 1. And partial n over x minus partial m over y divided by m equals 1 over 2xy plus y cubed, which is not a pure y function, so no mu of y. A powerful shortcut appears when m and n are homogeneous functions of the same degree. Recall, a function f of x comma y is homogeneous of degree n if f of lambda x, lambda y equals lambda to the n times f of x comma y. For such pairs, the expression mu equals 1 over xm plus yn acts as an integrating factor, provided xm plus yn is not equal to 0. The reasoning uses Euler's theorem. For a homogeneous function h of degree n, x partial x plus y partial y equals nh. Applying this to m and n, and after some algebra, one finds that the quantity open parenthesis partial m partial y minus partial n partial x close parenthesis divided by xm plus yn depends only on the ratio y over x, which can be treated as a function of the product xy, or of x to the n times y to the m when the degree is n. In many engineering problems, the governing differential equation comes from scaling laws. For example, pipe flow, heat transfer, and the terms are naturally homogeneous. Using mu equals 1 over xm plus yn instantly makes the equation exact, avoiding the trial and error search for mu of x or mu of y. Example, m equals x cubed y, n equals negative x squared y squared. Both are homogeneous of degree 4. Compute xm plus yn equals x times x cubed y plus y times negative x squared y squared equals x to the fourth y minus x squared. Y cubed equals x squared y times open parenthesis x squared minus y squared close parenthesis. The integrating factor mu equals 1 over open bracket xm plus yn close bracket equals 1 over open bracket x squared y times open parenthesis x squared minus y squared close parenthesis close bracket. Multiplying the original equation by mu yields an exact differential that can be integrated. If the homogeneous degree is n, sometimes mu can be expressed as a simple power of xy. For example, mu equals open parenthesis xy close parenthesis to the negative n minus 1. This is the reason textbooks list mu of xy or mu of x to the ny to the m. When none of the simpler cases work, we can attempt a general integrating factor mu of x comma y by examining the two ratios. R1 of x comma y equals the partial of m with respect to y minus the partial of n with respect to x, all over n. R2 of x comma y equals the partial of n with respect to x minus the partial of m with respect to y, all over m. If R1 simplifies to a function only of x, say f of x, then we set mu of x equals e to the integral of f of x dx. If R2 simplifies to a function only of y, say g of y, then mu of y equals e to the integral of g of y die. If neither reduces to a single variable, we may still be able to guess a form mu of x comma y equals x to the times y to the b, or mu equals open parenthesis xy close parenthesis to the k, and substitute back into the exactness condition to solve for the exponents of b, k. The systematic algorithm. Step 1. Compute the two ratios R1 and R2. Step 2. Look for dependence on a single variable. Step 3. If found, integrate to get mu. Step 4. If not, try a power law ansatz mu equals x to the y to the b. Step 5. Insert mu into the exactness condition. Partial of mu times m with respect to y equals partial of mu times n with respect to x, and solve for a and b. Step 6. Once mu is known, multiply the original equation and solve as an exact one. This approach is akin to adjusting the density of a material in both directions to neutralize any rotational component of the vector field, thereby creating a pure gradient field. Example: m equals open parenthesis 2y plus x close parenthesis divided by open parenthesis x squared plus y squared close parenthesis. N equals open parenthesis 2x minus y close parenthesis divided by open parenthesis x squared plus y squared close parenthesis. Compute R1 equals open parenthesis partial of m with respect to y minus partial of n with respect to x close parenthesis divided by n equals 0 divided by n equals 0, which depends only on x trivially. Hence mu equals e to the integral of 0 dx equals 1, so the equation is already exact. If we change m to open parenthesis 2y plus x close parenthesis divided by open parenthesis x squared plus y squared close parenthesis plus 1 over x, R1 becomes a messy function of both x and y. Then we try mu equals x to the y to the b and find a equals 1, b equals minus 1 works. After determining mu, the rest follows the exact equation procedure. Example 1 mu of x case. Given y e to the xy dx plus x e to the xy plus 1 dy equals 0. Step 1. Check exactness. Partial m with respect to y equals e to the xy plus xy e to the xy. Partial n with respect to x equals e to the xy plus xy e to the xy. The extra plus 1 in n does not change the derivative, so the two are not equal, therefore not exact. Step 2. Compute R1. The numerator partial m minus partial n is 0, divided by n gives 0. The difference is 0, so the equation is exact. The plus 1 does not affect the derivative with respect to x, therefore no integrating factor is needed. Step 3. Solve. Integrate m with respect to x. Psi equals the integral of y e to the xy dx, which is e to the xy plus h of y. Differentiate psi with respect to y, gives psi sub y equals x e to the xy plus h prime of y. Set this equal to n. X e to the xy plus h prime of y equals x e to the xy plus 1, so h prime of y equals 1, therefore h of y equals y. Implicit solution, e to the xy plus y equals constant. Example 2 mu of y case. Given 2xy plus y cubed dx plus x squared plus 3xy squared dy equals 0. Step 1. Exactness question. Partial m with respect to y equals 2x plus 3y squared. Partial n with respect to x equals 2x plus 3y squared. They are equal, so the equation is exact, no integrating factor is needed, and we solve directly. Psi equals the integral of 2xy plus y cubed dx, which is x squared y plus y cubed x plus h of y. Psi sub y equals x squared plus 3xy squared plus h prime of y. Set equal to n gives h prime of y equals 0, so h of y equals constant 1. Implicit solution, x squared y plus xy cubed equals constant. Example 3. Integrating factor of type mu equals 1 over open parenthesis xm plus yn close parenthesis. Given x cubed y dx minus x squared y squared dy equals 0. Step 1. Homogeneous question. Both terms have degree 4, therefore the equation is homogeneous. Compute mu as 1 divided by open parenthesis xm plus yn close parenthesis equals 1 over open bracket x times x cubed y plus y times negative x squared y squared close bracket equals 1 over open bracket x fourth y minus x squared y cubed close bracket equals 1 over x squared y times open parenthesis x squared minus y squared close parenthesis. Multiply the differential equation by mu, the new m tilde and n tilde become exact. This can be verified quickly. Integrate the new m tilde with respect to x and finish as usual, obtaining the implicit solution after simplification. These examples illustrate the decision tree. First, check if the equation is exact, if so solve it. If not, try an integrating factor that depends only on x or only on y. If that fails, look for homogeneity and use mu equals 1 over xm plus yn. Finally, resort to a general integrating factor that depends on both x and y. Explanation. Typical exam-style questions follow the same logical steps. Question 1. Verify whether the equation y cosine x dx plus sine x dy equals 0 is exact. If not, find an integrating factor that depends only on x and then obtain the implicit solution. A solution sketch. Compute partial m with respect to y equals cosine x. Partial n with respect to x equals cosine x, therefore exact. Integrate m. Psi equals y sine x plus h of y, differentiate psi sub y equals sine x plus h prime of y equals n, hence h prime of y equals 0. Final answer y sine x equals c. Question 2, 2xy plus y cubed dx plus x squared plus 3xy squared dy equals 0. Show it is not exact, find mu of y and solve. A solution sketch. Partial m with respect to y equals 2x plus 3y squared. Partial n with respect to x equals 2x plus 3y squared, therefore actually exact trick. No factor needed. Solution x squared y plus xy cubed equals c. Question 3, y plus 2x dx plus x minus 3y dy equals 0. Determine an integrating factor of the form mu equals x to the times y to the b. Solve the resulting exact equation. A solution sketch. Compute ratios, therefore neither depends on a single variable. Assume mu equals x to the times y to the b. After substitution, the exactness condition gives a equals 1, b equals -1. Thus mu equals x divided by y. Multiply x times y plus 2x divided by y dx plus x times x minus 3y divided by y dy equals 0. Now verify exactness, integrate, obtain implicit solution x squared plus xy minus 3y squared equals c. Question 4. For the homogeneous equation x squared minus y squared dx plus 2xy dy equals 0, find the integrating factor using mu equals 1 over open parenthesis xm plus yn close parenthesis, and write the solution. A solution sketch. Degree 2 homogeneous. Compute xm plus yn equals x times x squared minus y squared plus y times 2xy equals x cubed minus xy squared plus 2xy squared equals x cubed plus xy squared. Mu equals 1 over x cubed plus xy squared, which is 1 over x times open parenthesis x squared plus y squared close parenthesis. Multiply, integrate, final implicit solution y divided by x equals c, or equivalently y equals cx. These typical items test the student's ability to check exactness quickly using partial derivatives. Identify the right form of integrating factor, mu of x, mu of y, power law, or homogeneous. Perform the integration steps to recover psi of x, y. Present the answer in implicit form, often simplifying to a neat relation between x and y. Mastering the flow of decisions exact. Leads to mu of x or mu of y, then homogeneous, then general mu of x, y, will give you confidence in any exam question on exact differential equations.